So now that we know what it means to tricolor a knot, in other words, to take the arcs in a knot diagram and assign each one of those arcs one of three colors in such a way that at every crossing, all three arcs that are incident at that crossing either have the same color or they all have different colors. We know what that means. We know what it looks like. We know how to detect whether or not a certain coloring is valid or not. But what we don't yet have is a connection from coloration into something that's algebraic, something that can help us to get a handle on an algebraic structure that can encode colorability. That's our ultimate goal. And to get there, we need to figure out how to turn that observation about what a valid coloration of three colors is for a knot diagram into an equation that gets the whole ball rolling. So the question is, how do we use an equation to see that a knot is or is not three colorable? I call this equation the magic equation. So we're going to call our three colors 0, 1, and 2. You can think of them as red, green, and blue if you like, but we're going to use 0, 1, and 2 so that we can have a way of actually attaching numbers and algebra and equations to these. And what we want is an equation which is going to be true at every crossing that satisfies our condition, the condition that either all three colors are the same or all three colors are different. And that same equation also has to be false any time that a crossing fails to meet that criterion. So this magic equation is going to be true at every crossing if and only if we have a valid three coloring of our knot. So let's observe what that might look like. We want this magic equation to be true anytime all three colors are the same. So if x, y, and z are all 0, we want this equation to be true. If x, y, and z are all 1, or if x, y, and z are all 2. Those are the cases where all three colors are the same, and we want this equation to be satisfied. Likewise, we also want the same equation to be true when all three colors are different. So when x, y, and z are 0, 1, and 2, or any permutation thereof, we also want this same equation that we build to be true at those crossings too. And those are exactly the cases, all 9 of these. These are the 9 cases in which we want this equation to be true, and exactly those cases. All right, so what might we do? One of the observations we could make, I suppose, is that because this equation shouldn't be sensitive to any permutations of x, y, and z, the three colors that are meeting at a given crossing in an arc, because it needs to be symmetric with respect to any permutation of x, y, and z, we should be doing something to x, y, and z which is a symmetric operation. And so, most obvious thing might be to just add x, y, and z together. Addition being a commutative operation, it doesn't matter how we permute x, y, and z if what we're doing is adding x plus y plus c. So let's try that. If I add x plus y plus c for these 9 different combinations of x's, y's, and z's, then for all the combinations in which we have different colors, we're always adding a 0 plus a 1 plus a 2, and so that sum is always 3. And so we might think, well, maybe this magic equation can be x plus y plus z equals 3, because that seems to be satisfied exactly when all three colors are different at one of these crossings. But that pattern gets broken when we look at some of the all same cases up here at the top. Obviously, if I add 3 zeros, I don't get 3. I get 0. If I add a triplet of 2's, I get 6. So, all right, so there's something a little bit, we can't quite use x plus y plus z equals 3 for our magic equation, but a lot of our combinations do seem to satisfy that. So these are the 9 cases in which we need our equation to be true, and already we're seeing that there's some disagreement in what the sum of x plus y plus z is, but maybe we can patch that up. To see that that's true, let's look at the cases where we want this equation to be false. We want the equation to be false exactly when we don't have a tricoloration. In other words, when the conditions for tricolorability at a crossing are violated. And they're violated exactly when there are 2 different colors, but not 3 at a given crossing. And it turns out that there are 18 different combinations of 0s, 1s, and 2s in which that happens, right? I've arranged them into blocks. Here 2 of the colors are 0, but the third one is not. Here 2 of the colors are 1, but the third one is not. And then here 2 of the colors are 2, and the third color is not. So here are the 18 cases where we need the same equation to be false. And if our guess is that adding x plus y plus c together is going to be the operation we want, let's add x plus y plus c together in these 18 cases and see what we get. And if we do that, we find out that there's still some disagreement over here. But that it seems like there's some pattern. Anytime we have 2 colors being 0 and the third one not, we either get 1 or 2 for the sum of x, y, and z. We either get 2 or 4 for the sum of x, y, and z in the case where 2 of the colors are 1. And we either get 4 or 5 for the sum of x, y, and z in the case where 2 of the colors are equal to 2. And so let's just look back and forth between these two cases. Every time we want this equation to be false, the sum is either 1, 2, 4, or 5. Anytime we want this equation to be true, the sum is either 0, 3, or 6. So if we want an equation which is going to meet both of those criterion, we have to ask, what do the true cases have in common that the false cases do not? And the answer is that the sum, in all of the cases where we want this equation to be true, the sum of x, y, and z is not always the same, but it is always a multiple of 3. X plus y plus z equals 0, 3, or 6. All of those are multiples of 3, and all of the cases in which we need this equation to be false are not multiples of 3. 1, 2, 4, and 5. So the observation is that if we want an equation which is going to be true when we want it to be true and false when we need it to be false, then all we need to do is require that that sum of x, y, and z be a multiple of 3 exactly when this equation is true. And so the magic equation for tricolorability is that a knot is tricolorable if at every crossing I add x, y, and z, and the result is a multiple of 3. And a better way to say that, that's going to let us use more of the arithmetic and number theory and algebra that we know, is we'll say that x plus y plus z is a multiple of 3 when x plus y plus z is congruent to 0 mod 3. It's the definition of multiplication by 3, right? In other words, this just means that if I take x plus y plus z and I subtract 0 from it, that the result is a multiple of 3. So this is what we're going to call our magic equation for tricolorability. And it's the equation which we need to check at every single crossing in a knot diagram. If a knot diagram and a coloration of that knot diagram satisfies this equation at every crossing, then that is a tricoloration, a valid tricoloration of our knot. If this equation is violated at even one crossing, then we do not have a tricoloration of that knot. So just as an illustration, here's the figure 8, right? This is our 1' 4-crossing knot. And let's see what this equation would look like at all 4 crossings in this knot diagram if we just experiment with it a little bit. So if I take my 4 arcs and I just give them each a different name, I'm going to call them x1, x2, x3, and x4. And abusively, I'm going to use those also to refer to the colors that we assign to those 4 arcs. And we look at each crossing one at a time. Each of those crossings is going to give us an equation, which if that equation is true at that crossing, then we have a valid tricoloration condition at that crossing. And if it's not, then we don't. So at the first crossing, which I've labeled A up here, we have 3 arcs that are incident. x1 is our over arc, and x3 and x4 are our 2 under arcs. And so if this tricolorability magic equation is satisfied at crossing A, that must mean that the colors that we assign to x1, x3, and x4, when added together, need to be a multiple of 3. So at crossing A, the equation that we need to satisfy is x1 plus x3 plus x4 is congruent to 0. And then secretly over here, there should be a little mod 3. I just don't really have space to write that every time. And so what we observe is that every crossing is going to give me another equation, and then all those equations are pretty much going to look the same. At crossing B here, the 3 arcs that are incident are x3, which is our over arc, and x1 and x2, which are our under arcs. And so at that crossing, the equation that we need to be satisfied is x1 plus x2 plus x3 equals 0. Do the same thing for crossing C. Do the same thing for crossing D. So what you'll notice is that really all these 4 equations that we just wrote down are all the same in form. The only difference between these equations is which arcs are actually meeting at that crossing, right? X plus y plus z just labels which are the 3 colors that we're trying to test are either all the same or all different at each of these crossings. So what do we have? We have at the end of the day a system of 4 linear equations in 4 unknowns, and it just so happens that the arithmetic that we're doing here is not over the integers or the rational numbers, but is actually over the integers mod 3, right? And so what we would need to know is, does this system of equations have a solution? If we can find a solution for this system, that solution is a tricoloration of our knot. If the system doesn't have a solution, then there is no tricoloration for this knot. So let's see what happens if we try to solve this system of equations. Does it have a solution where x1, x2, x3, and x4 are all in the set 0, 1, 2 residues mod 3? So what we'll do, of course, is we'll row reduce. But when we row reduce, the arithmetic that we have to do for row reduction is arithmetic mod 3. So when I add 2 rows together, for example, I'm going to be adding them using addition mod 3. If I decide to multiply a row by a number, I'm going to be doing that multiplication also on the mod 3 basis. Now I'm going to spare you the details for now, but if we do this row reduction, we find out that the row echelon form for this 4x4 system looks like this. x1 minus x4 is congruent to 0, x2 minus x4 is congruent to 0, x3 minus x4 is congruent to 0, and then on our last row, we end up with 0 is congruent to 0. And in linear algebra, we remember that having a 0 equals 0 in my square system means that I don't have enough pivot columns to give me a pivot in every column. In other words, not all 4 of my variables are going to be bound variables. And since this is a homogeneous linear system, the right-hand sides are all 0, that must mean that we have not only a consistent system, but a system that has more than one solution. And what we can do is then express each one of my 3 bound variables, x1, x2, and x3, in terms of the variable which is not bound, the free variable, which is x4. So I'm just going to take and rearrange this system to express each of x1, x2, and x3 in terms of x4. And what we find out is that as soon as you choose for me an x4, in other words, choose how to color this arc that I've kind of labeled with the peach coloring here, as soon as I decide how to color this arc, then the only way to get another solution which meets tricolorability conditions is to color the first arc that same color the second arc that same color, and color the third arc that same color. So we have a solution, but the solution requires us to, once we choose a color for arc number 4, to color arcs 1, 2, and 3 all that same color. So what do we learn here? We learn that if we choose T, the color of my arc number 4, I can choose that T however I like. In other words, I have 3 choices for how to do that. Either T is 0, T is 1, or T is 2. Red, green, or blue. But as soon as I decide what color I want T to be, then all the other arcs in my diagram are going to have that same color. So what have we found out? All of these colorations are trivial. The only way to tricolor this knot, according to the algebra that we just did, is to color every one of its 4 arcs the same color. Which works. It's a tricoloration of this knot, but it doesn't use all 3 colors, 0, 1, and 2, so it's not an interesting tricoloration. So the only way to tricolor the figure 8 knot is to use the same color on every arc. And so that's not very interesting. We say that this this knot only has trivial tricoloration. So the figure 8 knot was a flop as far as tricolorability is concerned. But what we want to do next is push that envelope a little bit more and figure out how we can use tricolorability to distinguish between knots. So what happens when this system doesn't only have trivial solutions? Can it tell us more about the properties of the knot? And then to push that even a little bit further and say, what if we want to use more than 3 colors? How do we have to change the whole structure of the argument that we just made, or how much of it gets to remain the same?